Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit 13, Lesson Number 3, More Work with Matrices. So this is going to be our second and final lesson that gives a brief overview of what matrices are and how they're used. And today we're really going to get into their essential purpose, which is solving systems of equations. But first, let's start off with a review problem. All right. Exercise 1 says, find the following product, if possible. If not, explain why, and then modify. So originally, full disclosure, I had put this problem down on a worksheet, and I had messed up. See if you can figure out why that is. Think about it for a minute. All right. Well, based on our last lesson, if we look at this, this is a 2 by 2 matrix that is attempting to multiply a 3 by 2 matrix. And what we found out was that you can't multiply two matrices unless the number of columns in the first matrix is equal to the number of rows. Remember, what I'd be doing is I'd be taking this row and I'd be dotting it into this column. But that's not possible because, simply put, their dimensions don't match, right? So I can't do that. But if I flip-flopped them, right, if I had 4, -1, 2, 0, 0, 7, and then -2, 1, 3, -6, well, now I can actually find this product because this is now a 3 by 2 multiplying a 2 by 2. Whoops, that was weird. Multiplying a 2 by 2. I can now multiply them because those match. The beautiful thing is I also know the dimensions of my resulting matrix. It's going to also be a 3 by 2. It's going to have 3 rows and 2 columns. So it's going to kind of look like this one. That one. This one. Anyway, what I'd like you to do is pause the video for a minute and just remember that algorithm. And then we're going to do it on the calculator. I know. But seriously, the algorithm's important. So go ahead. All right, let's run through it again. The algorithm is weird, but let's do it. So I'm going to take this row and dot it into this column. So my first entry is going to be 4 times -2 plus -1 times 3. It's going to give me -8 minus 3, which is -11. Then I'm going to take this row and dot it into this column. So it's going to be 4 times 1 plus -1 times -6. That's 4 plus 6, and that's 10. Now, we've come to the end of our columns. So we move to the next row. We take this row, we multiply it by this column. So we'll get 2 times -2 plus 0 times 3, which is -4. Do that one in my head. Then I'll do this row times this column. Most linear algebra professors would literally use the word dot it. I'll dot this row into this column, right, and that gives me a +2. That 0 is helpful. Then I'll take this row and dot it into this column. That'll be 0 times -2 plus 7 times 3. That's, of course, 21. And then I'll take this row and I'll dot it into that column. 0 times 1 plus 7 times -6 gives me -42. All right, there it is, and notice it is a 3 by 2. Okay, there it is, a 3 by 2. Now this algorithm, and it really is an algorithm, take the row, dot it into the column, take the row, dot it into a column, is certainly something that one can program a computer to do. In fact, I still remember being in a basic computer programming course back in college, many centuries ago, and actually writing a program to do that. It's not really that hard. Lots of if-then loops, you know what I'm talking about, coders, right? So your graphing calculator can do this, all right? So I'm going to show you how it's done, all right? So it's been a little while, but let me do this first. Well, I'm going to leave that text there, okay, because I want to be able to come back. But let's open up our TI-84 Plus. All right, it's all open. Okay, so how in the world do we even find our matrix? Well, find the x to the minus 1 button, right? It's right over here, and right above that is the term matrix. Okay, so let's go in there. Notice that what we first see are these capital block letters, A, B, C, D. Very often matrices, for whatever reason, are given uppercase letters to distinguish them from vectors, which are often given lowercase letters, and of course arrows. But very often matrices, in fact I think almost every time I've ever seen them, have been designated with block capital letters. So what we're going to do is we're going to let this one, I think, be matrix A, and I think that we'll let, let's go red again, whatever, limited amount of colors here, and then I'll let that be B. So how do I enter them? Well, what I'm going to do is I'm going to take my calculator and I'm going to go over to the edit, all right, and I'm going to choose matrix A. Now what's kind of cool about that is the first thing that it wants to know is it wants to know the dimensions. Well, matrix A is a 3 by 2, so I enter 3 by 2, enter. And now the beautiful thing is I can just literally enter it by row. So in other words, the cursor is literally on the first entry of the first row. So I put in 4, enter, -1, enter. Notice it immediately goes to the next row. 2, enter, 0, enter, immediately goes to the next row. 0, enter, 7, enter. That's it. That's it. Now what I'm going to do is I'm going to kind of exit this, and I'm going to go in and I'm going to edit matrix B. All right, so let's go into matrix B. It wants to know what its size is. It's a 2 by 2. So there we go. All right, now what I'm going to do is I'm going to put in -2, enter, 1, enter, 3, enter. I can even do it without hands. -6, enter. Woohoo! And now I'm going to actually get out of this. I'm going to go back to the main screen. I'm out of here. So what I literally want to tell the calculator to do right now is I want to tell it to do A times B. So what I'm going to do is I'm going to go in, go back into my matrix menu, and I'm just going to grab A. I'm going to hit enter on A. I'm back out to the main screen now. Now I'm going to use the multiplication symbol, although you don't have to. Like multiplying all things, if you just put them side by side, the assumption is multiplying. So I've put in A, I'm going to go back in, grab B, and I'm going to hit enter. Now, depending on which TI model you're looking at, it may be easier or harder to really look at it, but you should be able to see that resultant matrix. That -11, 10, -4, 2, 21, -42. There it is. Now, a couple things. All right, couple things. Try this really quickly on your calculator. Try to do B times A. See what happens. Gives you an error, right? Yeah. And even the name of the error is instructive, right? Because what it's indicating is it can't even do the multiplication. It can't even do the multiplication, right? So that tells me one thing for certain. Multiplication of matrices is not commutative. Now, we probably already figured that out yesterday, but it can't be done. It's kind of important to understand something. A lot of students think, well, now that I know how to do it on the calculator, and I know I'm going to have the calculator on my on the SAT Math Level 2 exam, well, then I don't need to know the algorithm. Trust me, there are many, many ways that they can test whether or not you know the algorithm, even if you've got your calculator. All right? So know the algorithm. It will be tested, I bet. All right, I'm going to clear all this out. All right, and let's move on. Okay, the next topic, just out of right field. I mean, it's just, okay, but wait, what? Is what's known as the determinant of a matrix. All right? Again, remember, we are abbreviating so much right now, so it's kind of difficult to even explain what the determinant is, other than the fact that it's important. One can almost think of the determinant as being the magnitude of the matrix. I know that a lot of people would disagree with me on that, but it's a good way to kind of think about it. It is, if you will, the size of the matrix. It's kind of like the magnitude of the vector, except it's the size. We symbolize the determinant by using vertical bars. Now, the determinant of a 2 by 2 matrix, again, has this kind of weird algorithm to it. Trust me, once we get into a 3 by 3, very weird. And we symbolize the determinant with absolute value bars again. I'm going to be very clear, that's a vertical bar. It almost looks like I've got a little bit of a bracket there, and I don't. Okay? Vertical bars only. Here's how you do it. You take this and you multiply it by this, all with subtraction, this times this. So I get 12 minus 4, and the determinant is 8. Whatever that means. Okay? So real quickly, find the determinant for b. Use the symbolism itself. I know that the calculation's easy, but write down those absolute value bars again. It'll help you remember what they mean. All right. It's a simple calculation, right? Because, nice. -1, 7, -6, 8. Stray marks everywhere. Literally, this times this, which is -8, minus this times this, which is -42. Be careful there. Negative gives me a positive 34. Now, determinants can only be found for what are called square matrices. They have no physical basis and cannot be calculated for anything but a square matrix. A 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5, even a 1 by 1. Although that wouldn't be very interesting. The standard algorithm for finding the determinant of a 2 by 2, that's it. You know, a lot of times people even give a formula because a generic 2 by 2 looks like this, A, B, C, D. And oftentimes they'll say the determinant is A times D minus B times C. That's the determinant, right? Yeah, whatever. You know, let me clear this out because then we're going to look at the 3 by 3. Now again, this is all kind of guesswork on my part. In other words, you know, will this show up? Will it not show up on the SAT level 2? I don't know. But I do know things like multiplying matrices and the determinant of matrices are very, very important. So if something's going to come up, that's it. So what we're going to do in this problem is we're going to look at the standard way of finding the determinant of a 3 by 3. What we're going to use is what's a procedure called expansion by minors. There's absolutely no need to memorize that term, expansion by minors, but it is weird. So here's how it works. Okay, so strange. We're going to grab any row or any column. Any row or column gets the job done. Any row or column. Any row or column. Any row or column. Okay, but I'm going to pick the first row just to not confuse you, because this is confusing enough anyway. And I'm going to pick the first element of that row. Now what I'm going to do is I'm going to literally eliminate the column that it's part of and eliminate the row that's part of. What I'm left with is a 2 by 2 matrix. Now I'm actually going to write it down as a determinant. Okay? Now, I know this is going to seem very weird, but then I have to go to subtraction. I'm going to alternate addition and subtraction. And now what I'm going to do is I'm going to erase all of this. And I'm going to go back to blue. Yep. I'm going to circle my row again, and this time I'm grabbing the 5. Okay, and then I'm going to eliminate the column and the row that it's in. That leaves me with the determinant 7, 0, -4, 1. All right. Then I'm going to erase all of this. And I'm going to go back to blue. And I'm going to grab the -1. Now, technically, oops, I wanted to go to blue. Technically, what I really have is I have plus -1 times, again, eliminate, the matrix 7, -3, -4, 2. So I alternate. Now, one of the things that's tricky is if you were to start with the second row, you'd have to start with -7, all right? And then plus -3, and then -0, all right? It's safest to just stick with the first row or the first column. Now here's the key. I already know how to do this matrix, or I already know how to do that determinant. I'm going to go back to blue, I think. It's easier to see on the screen. Right, this thing is -3 times 1 minus 0 times 2. right? This one is 7 times 1 minus negative 4 times 0. I know that looks weird. And this is negative 1 times 7 times 2 minus negative 4 times negative 3. Oof. Let's clear these things up. That's gone, so I get 2 times negative 3 minus 5 times 7 minus 1 times, what do I have here? 14. That's 12. Look at this, I got the triple negative. I never get the triple negative. Anyway, 14 minus 12, I get excited about the weirdest things. My students can tell you that. Ooh, negative 41, negative 43. Now, you might look at that and go, wait a second, Mr. Weiler, you were talking about absolute value, determinants are like magnitudes, and suddenly I have a negative. Determinants can absolutely, positively be negative. There's no reason why a determinant can't be negative. The negative does have something to do with what's going on with matrices. It kind of indicates, if you will, a reflection in terms of their geometry, but don't get overly worried about that. You can probably tell how by using the method of expansion by minors. You could now find conceivably the determinant of any square matrix. Any square matrix. I mean, but think about it. Think about how bad it would be. I'm going to clear this out, so write down anything you need to. All right, here it goes. Imagine you had a 4 by 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. You know, apparently just wavy stuff in it. Anyway, the way you would do it is you'd literally pick this row, and then you'd pick this thing. And then what would happen is you'd have a 3 by 3. And then minus, and you'd do the next one, and then you'd have another 3 by 3. But the thing is, to evaluate the 3 by 3s, you'd have to do them by expansion by minors. It would just get ugly. Ugly, ugly, ugly. And of course, there is a way that your calculator can do this. So we're going to take a look at that. All right. In fact, let me clear all of this out. And let me bring out our TI-84 Plus again. Hello, calculator. Okay, so let's go back into our matrix menu. Let's go over to edit. I said we just put it back in matrix A, might as well. So let's go over to matrix A. Matrix A now is a 3 by 3, so dimension it. I know that there's some things that are already in it, but that's okay. We'll just write over. And now let's enter it. Let's do 2 and 5, negative 1, 7, negative 3, and 0, negative 4, 2, and 1. I love it because it just matrices fill up by the row. First row, second row, third row. All right, now let's exit. All right, now I'm back up to the main screen. Now I'm going to go back into the matrix menu, and I'm going to go over to the calculate submenu. I'm going to go over to where I can find things out about my matrix. So if I go over, one of the things I find is a little thing called determinant, D-E-T. So go, grab that. Now it's leaving me a space to put in what I'm finding the determinant of. So let's go back in and grab matrix A. Got it? Okay. Let's get out of here. Let's hit enter. And there's our negative 43. Now again, just like with the multiplication, the SAT knows that your calculator can do this. So if they're going to ask you something about matrices, it's unlikely that it's going to be just a straightforward calculation, but it's going to have something to do with knowing the algorithm. So know the algorithm for the 2 by 2 and maybe the 3 by 3 determinant, and don't worry about it past that. Okay, so now we're going to come back to the most important thing, in my humble opinion, about matrices. Matrices allow us, especially when we have technology, to solve systems of equations regardless of how many equations and unknowns that we have. All right, so we are right back to where we began, all of in the last lesson. It says set up a matrix representation for this system. So here we go. 2, 1, 3, those are the coefficients. 1, negative 5, 1, coefficients. Negative 4, 5, negative 3. X, Y, Z equals 13, 14, and negative 19. Now, when we set this up yesterday, you had no clue about it at all. They were just brackets, symbols, things like that. But now think about what you know in terms of multiplying matrices. This is a 3 by 3 multiplying a 3 by 1, and that means it's allowed because those match, and it should result in a 3 by 1, and that's exactly what we have. Also notice if we actually did the multiplication on the left-hand side, right? The first thing I would do is I would multiply, I'm so hesitant to draw this in, but the first thing I would do is multiply this by this, and I'd set it equal to this, right? It would be 2 times x, 1 times y, 3 times z, and that would be equal to the first entrance in this matrix, and that's exactly it, right? 2 times x, 1 times y, 3 times, whoops, that's supposed to be a z. Sorry about that, it's supposed to be a z, is equal to 13. Then we would do 1 times x, negative 5 times y, 1 times z equals 14. Negative 4 times x, 5 times y, negative 3 times z is negative 19. All right, so consistent. Now letter B says solve this system by applying the inverse matrix to both sides of your answers to part A. For a moment, forget about this. Just don't worry about it. All right, let's solve this equation. 4x equals 20. Now, I know we all can get the answer. It's x equals 5. And I know almost everybody would, everybody would think about the answer as, divide both sides by 4. But one of the ways you could think about it is you could say, well, actually, let me do it on a separate line. I could multiply by 1/4 on both sides. In fact, what that's the equivalent of is multiplying by 4 to the negative 1. And of course, what that means is these two would actually cancel, and this would leave me with 5. What we've got really up above now is we've got almost the analogous situation. We've got matrix A times, what should I call that? Most of the time people will call it a vector, vector x, and then that's sort of equal to vector B. Now, we're going to actually have to put this one in as a matrix all on its own. So how do I really want to think about this? That's questionable, right? But we're going to put this in as a matrix, we're going to put this in as a matrix. The beautiful thing is we're going to solve it by just multiplying by the inverse matrix on both sides. Now notice I was trying to be very careful. I didn't put that multiplication on the right-hand side because multiplying two matrices is not commutative. So in your calculator, let's do this. For A, let's put in our big matrix, our 2, 1, 3, 1, negative 5, 1, negative 4, 5, negative 3. In B, let's put in 13, 14, and negative 19. And what we're going to find out is that x, y, z is just going to be A inverse times B. But the first thing that we have to do is get all of that in there. So, all right, let's do it one more time. Let's open up the TI-84 Plus. Here it is. Okay, let's go into A. Let's modify it so it's a 3 by 3. Actually, it's already a 3 by 3. Let's put in our coefficients. Here we go. 2, 1, 3, 1, negative 5, 1. You should be faster than me at this. I got to do this on a computer. Negative 4, 5, negative 3. Although I can do it without my hands. Again, watch this. Let's now enter B. Right, we got A. So let's go over. Let's get into matrix B. All right, let's put in its dimensions. It's a 3 by 1. All right, without using my hands at all, I can put in 13, 14, and negative 19. It's magic. Actually, it's not. I got somebody over here who's doing it for me. That's not even true. Anyway, so I've got A and B in now. Let's get back out to the main screen. All right, and now let's literally type in A inverse times B. Right? So let's go into the matrix again. Let's grab A. We're now back at the main screen, and let's actually hit that x to the minus 1 button. That gives me A inverse. Let's multiply it by B, and let's hit enter. And look what it gives me. it gives me the following vector: -3, -2, and 7. So x is -3, y is -2, and z is 7. Awesome! And pretty easily checked too. Now, especially for my students, I want you to reflect back on how much easier this was than doing this back with the sort of the hardcore algebra that we did back in Unit 2. That was long, prone to error. This is very, very simple. And you know what? It would be just as simple if we had 4 equations with 4 unknowns, 5 equations with 5 unknowns, etc. All right, very, very simple. Okay, let me clear this out. Let's go on and do the last problem. Actually, there's a couple more. But now they're actually relatively simple, right? Because all I have to do is solve it by setting up a system, okay? So why don't you go ahead and set up the system for that 4x4. Ooh, 4x4, a little tricky, but takes a little more work, and then we'll go through it really fast, okay? All right, let's go through it. I'm not going to bring up the TI-84. We'll just eventually get the answer. For my own students, this is the work I'd love to see. I want to see your matrix. Sure, this takes time, but a lot less time than sort of solving it would have been the long way. W, X, Y, Z. We so rarely use W. 21, 57, -41, 48. Whoops, almost didn't get that in there. Then this is what I want my kids to do. Let me know that's A. Let me know that's B. And then let me know that, whoops, sorry, W, X, Y, Z is equal to A inverse times B. It's important to write it that way. You can't have B times A inverse. It won't even work. And then tell me what they're equal to. And in this case, it was 4, 7, -2, and -6. When engineers design bridges, which have truss structures in them, like this, every single node has 3 equations at least, and that's in a 2-dimensional structure. 3 dimensions, oh my goodness. But each one of these nodes has 3 equations and 3 unknowns for each one of the members coming into it. So this one node would actually have 9 equations with 9 unknowns. That would be a beast to solve by hand. On the other hand, when you have a system of matrices, it's very, very easy. Now there's a lot of open questions. How do we find the inverse matrix? That requires a lot of work, very, very ugly. And again, something that obviously you can program a calculator to do. Okay, so let me clear this out, and let's do one last problem. Okay, number 7 says, what happens when you try to solve the following system using matrices? All right, what is the value of the determinant of the square matrix? So it's kind of weird because generally speaking, if we have the same number of equations as we have unknowns, we tend to be okay. There tends to be a solution. But something funny is going to happen here. So attempt to solve this using your calculator. All right, and then we'll talk about it, and then we'll talk about the determinant. Okay. All right, let's go through it. So if you set up this 3, 8, -1, -2, 1, 7, -2, 20, 26 times x, y, z equals 65, -18, and 58. If we put that in A, and we put that in B, and then we do A inverse times B, what we get, at least on my TI-84, is error, something that says singular MAT, singular matrix, singular matrix. What's a singular matrix? Well, the key here is actually looking at the value of the determinant. So if you haven't done this yet, take a moment and figure out what the determinant of A is just using your calculator. Don't use the technique we used earlier. Excuse me, bit of a chest cold. All right. Determinant was 0. And that will happen. When the determinant of a matrix is equal to 0, the system has no unique solution. All right. One can kind of think about it as dividing by 0, although that would be a little bit off, but it's fair enough. So if you were to encounter a SAT question where they simply gave you a bunch of systems and said which one doesn't have a solution, the best thing to do is have your calculator calculate the determinant of each one of the systems to figure out if it's equal to 0. All right, I'm going to clear this out. And let's finish up. All right, so that's it. That was our second mini lesson on matrices. Hopefully it's enough so that if matrix problems come up on the SAT Level 2, you have some ability to deal with them, both mechanically using your calculator, standard algorithms, especially finding the determinant of the 2 by 2 matrix and finding any product, know that algorithm. Besides that, though, that is that. That's our little unit to prepare us for the SAT Level 2. For now, let me remind you that this has been another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.